Assalamualaikum. This is topic 210, steady descent and glide. This will be the last part of the what we call unaccelerated flight performance. And after this, we'll move on to the new chapter. But before that, we will discuss about, we will have a case study about various designs of aircraft. But for the time being, let's focus on steady descent and glide. Now, descent and glide is basically an opposite to the steady glide. And first thing, let's look at the free body diagram of the aircraft. If you look at this, okay. Now we have lift, okay. We have drag, we have weight, and we have thrust. Now, one thing you notice that there is another one that we call normal force. Now, this normal force is basically a combination of lift and drag. Okay, it's a combination of lift and drag, and this is what we call normal force. Okay, now if you look at the axis, the body orientation. Okay, first thing is the body is at theta or pitch attitude with respect to the local horizon, but the aircraft is moving in the direction of a relative wind. Okay, the direction of wind at the angle of gamma or trajectory angle, okay, with respect to local horizon. So this actually shows that although the body of the aircraft is heading upward, its motion is actually heading downward with respect to local horizon. So this is a typical of aircraft descending on the, for example, on the landing approach, where it usually flies at high angle of attack. So in this case, the angle of attack is theta, okay, plus gamma, or the flight path angle or the trajectory angle. So the lift, it must be perpendicular to the direction of the wind or direction of the trajectory of the aircraft, while the drag must be parallel to it. The weight is always perpendicular to the local horizon because that's the direction of the gravity. Okay, and the thrust follows the direction of the body because the engine is attached to the body or the aircraft. Okay, so for steady powered descent, okay, so based on this free body diagram, we come up with the equation of motion, and this for the first one, it will be in the direction of the x-axis of the wind, this direction. So this is the equation. Okay, the thrust available, okay, cosine angle of attack, plus the weight sine gamma minus the drag, and that is mass times acceleration in x. Okay, the x of the wind axis. The second equation will be in the z direction. Okay, thrust available cosine alpha plus mg sine gamma minus half rho v squared SC. Sorry, this is not the second equation. This is still the first equation, but it's the extension of drag. Okay, now when it says steady, meaning that the acceleration is zero. Okay, so the aircraft is moving, going downwards, and it has already reached its terminal velocity, so there is no acceleration. So m dv over dt, and that is equal to 0. dv over dt is basically an acceleration. Okay, and in this case, dv over dt is equal to 0. The mass is not going to be 0. The mass is always that. Okay, it's equal to 0. So 0 acceleration. Now, the second equation is in z direction and perpendicular to the wing, to the direction of lift. So thrust available sine alpha plus lift minus w cosine gamma, and it's equal to mass times acceleration. And again, this is also steady, so there is 0 acceleration. Okay, not some acceleration, but 0 acceleration in this direction, 0 acceleration. Now take note that weight is equal to mass times gravity, acceleration, and CD is equal to KCL squared plus CD naught. lift is equal to this equation, and drag is equal to this equation. Okay, so we have two equations, and the third equation will be the kinematics equation, which is the rate of descent. Okay, and rate of descent is defined as the velocity, forward velocity of the aircraft, which is this velocity, okay, times sine gamma. So, which is basically the vertical component of the aircraft velocity. Okay, and that is rate of descent. Okay, now again, go back to this equation. Now, assuming the angle of attack is not huge, and this is what we call steady descent and glide. So the alpha is near zero. Okay, for steady unpowered glide. So zero acceleration. So this the first equation is simplified into W sine gamma minus D. Okay, so if you go back to this equation, you have this thrust available cosine alpha. Now assume that cosine alpha is small. Actually, you have this. Okay, you have thrust available. Okay, actually you have this thrust available. Okay, because this will become 1. Alright, but it's stated here this is unpowered glide. Okay, so obviously in the first slide it is different than the second one. Okay, only in terms of thrust. So the first one, if you have thrust available, meaning that while you are descending, you have a huge thrust, then this will not, we cannot abaikan this one lah, cannot neglect this. Okay, even if your alpha is small. However, in this case, for the second one, if you have unpowered glide, meaning that you do not you set your throttle to 0 or near 0, okay, and the thrust available term is drop also lah, tak ada. Okay, so we count this. So in case assume the aircraft is only gliding, so with no thrust, then the equation is reduced to only this. Okay, so similar in the z direction. So you have one equation in W sine gamma equal to D and W cosine gamma equal to L. Now combination of these two equations in x and z direction. So if you divide the sine over cosine, you get tangent. Okay, and if tangent gamma is 1 over lift to drag ratio, L over D. Okay, L over D. Now, what does this thing mean? Meaning that the angle gamma depends on your lift to drag ratio, or your lift to drag ratio depends on the angle of gamma. So either way, the higher the lift to drag ratio, okay, the smaller your gamma, meaning that you can glide, okay, at very minimal flight path angle if you have a high or maximum lift to drag ratio. Okay. Simple. Okay, so again this equation below prove this. Okay, so meaning that your ability to glide, okay, the gamma, okay, for unpowered glide only depends on the aerodynamics of your aircraft. So kalau you buat, contoh kalau you buat terbang kertas kan, it's a glider kan. Okay. So if you want to minimize the rate of sink, okay, the rate of the jatuh, you try to minimize the gamma. So the way you minimize the gamma is to maximize the lift drag ratio of the aircraft. So it is very logical that aircraft yang ada wing yang sangat panjang, long wingspan, very slim chord, okay, so aspect ratio tinggi, high aspect ratio wing will give you the highest lift to drag ratio, and hence the gamma is small. So that's the reason why that kind of aircraft is called a sailplane, because you actually do not need any thrust while you are gliding on air at high altitude. You don't need to thrust. Okay, you just find the wind. Okay, that can give you an upward movement. Okay, gust wind or thermal that can give you upward movement. It will go up. It will soar up again. Okay, it will soar up again, and later on it can glide with a minimum sink angle or a rate of descent, minimum gamma. Okay, uh, let's move. Okay, so this is the graphical look at. If you look at the gamma, okay, u is the forward speed with respect to the horizon, while v is the actual speed, the actual direction of air velocity, and the gamma is the sink angle or the descent angle. Okay, so if you begin with this point, the glide distance depends on gamma. So how far you can glide or how long in terms of time you can glide depend on gamma. Okay, in this case, the smaller the gamma, okay, the farther your glide distance, because the smaller the gamma, the lower the glide sync. But it also depends on the velocity v. If your v is fast, then you still sink at high descent rate. So you have to fly at the lowest velocity possible and the smallest gamma possible for you to have the longest, the longest time for glide. Okay, so in terms of glide distance, it depends on the v. Okay, you want to have to minimize the gamma, but you want to have to maximize the v. Okay, so that you can have glide distance, far glide distance. Okay, now if you look at it, it's a minimum gamma depends on 1 over L over D max. Okay, in which L over D max is equal to 4 CD naught K, or square root of all things. Okay, 1 over 4 CD naught K, square root of it. So 1 over L D max will become this. Okay, so this is Y minimum. Okay, now let's say altitude difference or the glide sync is low. So if you know the glide sync and the HG, okay, which is the sync altitude, okay, the altitude, okay, glide sync is V sine gamma minimum delta t, and you can find the time to glide, okay, the time to glide. The Hg is the altitude, okay, the altitude is the glide sync. Or and if you want to find glide distance, is S equal to V cosine gamma minimum times the time. Okay, so you get the glide distance, okay, or simply this hg over tangent gamma minimum. Okay, so this is basically the kinematics, okay, kinematics part of it. Now one question is minimum glide angle means minimum rate of descent? Okay, is minimum glide angle means minimum rate of descent? Actually, I have mentioned it just now. Okay, all right. So let's discuss this. Okay, with your peers, or you can discuss it with me later. Okay, if you are more interested, or if you have more interest on this, I can surely discuss about this. Okay, after this we'll look at the special cases. But before that, selamat bersahur. Okay, thank you very much, and I'll see you around.